He's writing papers at higher quality and higher speed than me today. He's only written 7 books by now. Out of which I think 6 are very difficult to read. But the 7th one, I can give you my own example. It's a beautiful read and you can actually zip past through into essential or element. It's called essentially
elementary
concept. Worth a while for most graduates to have a copy of it. Sorry? Not audible. Okay, I'm audible now. Okay, so the thunder is already lost. So let me just, without further ado, give you Borkar.
Okay. So thanks for the invitation. So let's see if this works. Not on. Okay. I think it was not on.
It's on.
But it was not clicking. Thank you. Okay, so that's the outline, and it's kind of a not somewhat remote topic from mainstream machine learning. So I have included a list of things which I have to introduce, and as it says, the introductions are very short. If you have not been exposed to it, you will pick up some jargon, but I don't think the time is enough to do a good job of introducing all of it. But I hope that it's not too little either. So let me start with the Markov decision proofs. What I want. Yeah. Yeah. So the first topic is Markov decision process. So even before I start on that, this is the one line summary which I did. So the Markov decision, the reinforcement learning is actually machine learning for dynamical systems, something evolving in time. You're trying to control them or at least learn what they are doing. So there's this time element. And what you have is instead of the usual input output of observations, you have the states. You are observing the states or something related to the states. And there, of course, if you are actually trying to control something in real time, it's an online scheme. Otherwise, you're just simulating it offline, which is of course easier generally. I mean, the mathematically better. You can play with it without risking any serious offshoots. So these are these two non-trivial distinctions: offline algorithms and online algorithms. And finally, this one-line summary of what reinforcement learning amounts to mathematically. So for Markov decision process, there are the classical area going back to 60s or maybe even before. And there are many things were done quite early. So the numerical schemes, the recursive algorithms for solving them and so on. That involves some conditional averaging. You work with Markov chains, so there's a transition kernel, and all these algorithms, each step you do some conditional averaging. And on the other side, there's a stochastic approximation, which I'll introduce. It's this, again, that even older, goes back to 1951, to be precise. And there you actually, it's kind of generalization of strong law of large numbers in a sense. You are recursively averaging out some noise out of some computation. So you combine the two and you get reinforcement learning. So the way it goes is that you have Markov decision theoretic algorithms where there's a conditional average. Now, if you are not, if you want to build an algorithm based on samples alone, you can't do that. Of course, there are people who, there are some schemes based on actual averaging as part of the algorithm. But suppose you don't want to do that, you just plug in a sample. But if you just plug in a sample, it will become sort of too random, something like a correlated random walk. So you need to do averaging. So instead of, so I have my equation x equal to fx. That's the original equation. My algorithm is xn plus 1 is fxn. That's the Markov decision theoretic algorithm. Then fxn involves an average. So instead of that average, I plug in a current observation. But then if I had fxn plus 1 equal to some g of xn comma psi n plus 1, that can be too random. I mean, so what you do is xn plus 1 is xn plus some small step size an times the correction gxn psi n plus 1 minus xn. So that's the way you get averaging. So the stochastic approximation is there for averaging, and otherwise it's just some Markov decision theoretic algorithm except for the conditional expectation. So that expectation is done by stochastic approximation. Okay, so Markov decision process is also called controlled Markov chains. So you have some state process xn on a finite state spaces, and also assume that control process un is also text finitely many values. These are not essential, but I think when you finally anyway you end up implementing finite objects, so you might as well stick to it. And all the nice theory is for finite case. And the defining equation is what has been displayed there. So the idea is that if you are at xn and you choose control un, then the probability that next time you are in j, xn plus 1 equal to j, depends only on xn and un, doesn't depend on the entire path. That's the Markov part of it, except that it's controlled Markov because the un is also there. So this probability xn plus 1 equal to j given the entire path till n is small p of j given xn un, where small p given I comma u, that function is prescribed. It's the control transient probability function. And we'll assume that it's time independent. There's no p sub n. I mean, each time is the same probability. And then the objective is to minimize some cost function. So there's some c from state cross function of state and current state and current control. It can also depend on the next state that adds some extra notation and doesn't change much. So you want to minimize the cumulative cost till time t minus 1 plus a terminal cost if it's a finite horizon. And then the standard approach is dynamic programming, which probably most of you know. So this is a 2-line description of the dynamic programming principle, a verbal description. Say that if you are at time n, you can look at the minimum cost for the remaining horizon. Then there's the minimum of a sum of two things: minimum of what you pay right now, plus the minimum from next time onwards. Okay, so that's intuitively clear. So the minimum cost to go at time n is the minimum of the immediate cost at time n, plus the minimum cost from time n plus 1 onwards. So this statement itself implies a backward recursion. So if you know minimum cost to go at time n plus 1, you can compute what it is at time n. And so if I define vi comma t, that's called a value function. So the minimum cost to go at starting from state I at time t. It depends on two things, time and the state. I think there's a t missing. Yeah, sorry. The second line there should be vi comma t. I don't know which version I have. I had corrected these. multiple versions floating. Anyway, now I'll stick to this. It's too late to back off. So it should be vi comma t is minimum of u of ci comma u plus one step conditional expectation of vj comma t plus 1. Okay. And of course, the terminal condition at time capital T you are done, so you just pay I. So vi comma t is hi. There's no future. There's a dead end. So you can start with vi comma capital T for all I, which is hi, the terminal condition, and then do this recursion backwards and then get all vi comma t. And then the important thing is the second bullet, the minimum u. So if vi comma t is obtained by doing that minimization, that u as a function of I, that minimizes it. That's the optimal choice at state I. That's easy to prove. I mean, you simply, if the minimum is attained at ui, say, so then vi I comma t is without the minimum c I comma ui t I comma t plus sum over j pj given I comma u I comma t vj t plus 1. That's a linear equation. do it, recurse it backwards, you get the total cost for that control. For any other control, there will be an inequality, so you cannot do better. That's the proof. So yeah, and once you plug this optimal choice in, that is u take u at time m to be v of xm comma m, then this xn becomes a Markov chain. Except that the transition probability for this Markov chain is p of j given I comma u I comma t. So it's a time inhomogeneous Markov chain, and that's because of finite horizon problem. The future depends on. I mean, the future ends at t. I mean, there's a well-defined dead end. So at time small t, you know how much time is left. It's not the same each time. So it's natural that the control should depend on time t. Now, this I am not going to, actually I'll be doing infinite horizon thing, where I'm not going to justify it. The finite horizon is easier to explain. So this discounted cost is another popular cost for infinite horizon, very popular with machine learning because it's easier to handle compared to what comes later. And here alpha is it's an infinite horizon, but you discount the future. The parameter alpha is something between 0 and 1. And then the dynamic programming equation is simpler. It's actually, there's no time dependence because at time t, I look at the entire future and I look at the entire future today and tomorrow is the same, assuming that it's long enough, assuming that it's infinite. So there's no reason that there should be a time dependent unless it depends explicitly on time, and we generally don't take it that way. And it's also popular in anything involving money because, in fact, alpha is often 1 by 1 plus interest rate because money spent today is worth more than if you spend it tomorrow. So it's very popular in sort of inventory control, finance, and all such areas. And then the minimum will minimizing the optimal control policy will depend only on the current state, not on either time or anything else. And this is the one I will work with. This is the long run average. This cannot be justified. See, this I am taking time average. So I cannot say t and next time, because any finite string doesn't matter. It's irrelevant. So you have to go through a limiting process, and you get this somewhat more complicated dynamic programming equation. There's this strange thing. So of course the alpha has disappeared, and there's no discounting. So entire future time has the same level of importance. But that minus beta has appeared, and that can be seen to be actually the minimum cost. It's not hard to prove. And the way you derive this is you kind of take a vanishing discount limit in the discounted cost equation, and you have to kind of renormalize it each time by subtracting off something. It's a little messier, but it works. Now, the other problem with this is that this solution, now if I add a constant to the vector v, you will still it will still solve the equation. So this here beta is unique. It's both are unknowns, v and beta, but beta is uniquely specified as the minimum cost. V is unique only up to an additive constant of the, under some irreducibility assumption. That means you can go from any part of the state space to anywhere else. Again, the minimizer vi doesn't depend on time, so it leads to if I use un equal to v of xn, it's a time homogeneous Markov chain. Now there, I have stated the algorithms for average cost only, which is actually more complicated, but that's what I'm going to use later. So there's something called relative value iteration, which does this. Basically, you start with some, so it's called value iteration because you start with a guess for the value function v0 of I, and then just keep iterating this. And then you can show that it will converge to the solution v of the dynamic programming equation, so that v I naught is equal to beta. So it goes to a unique limit. Once I specify, because v is unique up to a constant, if I specify it at any one value, it becomes unique. So this will converge to v I naught equal to beta, and that v and I naught will converge to beta. In fact, that's not a, probably say that later. No, I don't. Maybe I do later somewhere. The v and I naught is that offset. Okay, you have to see. This is not a see that damping factor alpha in discounted dynamic programming makes the iteration stable. It's what's called a contraction map. This is not. So there's no reason it will, if you just keep iterating without the Vn I naught, it won't converge. So you have to keep subtracting of something all the time. So if you subtract Vn I naught, it will the solution will converge to beta. You can subtract the average of Vn I over I, it will subtract to the solution where the average is equal to beta naught. You can subtract the minimum of Vn I, it will converge to the solution where the minimum of V is beta, and so on. Okay. So that choice is not unique. Now, yeah. No, so if I don't have Vn I naught, it's not a stable iteration. No, it converges. So whatever I subtract from here, it will converge to that value of V where this converges to beta. So because I've subtracted Vn I naught, it converges to the V where Vn I naught is beta. If I minimize minimum of Vni, it will converge to the V where minimum of Vi is beta. But you have that you cannot subtract anything. It has to be positively one homogeneous. And so there are some conditions on that. You can characterize what can be subtracted. There are certain choices. This is this has some advantage and one major advantage and one major disadvantage. This is simple. You don't have to look at the whole state space. Just fix a state space and hmm. Hmm. Yeah, but the VN will, yeah, so you are wasting effort actually if you already know the, yeah. Hmm. No, actually, what I was about to say is that this is good choice because it's easier. You have to read off only one state, but it's very bad because the information doesn't propagate fast. If it's a if it's a large Markov chain with only local connections, you are looking at only one state. And when you change Vn I naught to Vn plus one I naught, that effect does not percolate fast enough throughout the state space, so it's slow. Whereas if I do min or max, that takes care of the entire V. But then the problem is that you have to compute min or max for a large state space each time. I don't know whether anybody has studied it. In terms of convergence, this will be bad, but it's easier to implement. So this is policy iteration, which is basically here you iterate in the policy space. So start with some guess of policy, small v. So small v is the sort of, I'm taking un as some function v of xn, so that v. And at each step n, I fix that policy vni, and then the dynamic programming equation becomes like a fixed control equation, so it's linear. So solve that linear system. That gives you Vn. Then given Vn, you pick Vn plus 1 by minimizing the right-hand side of the what would be the dynamic programming equation. And this for a finite state, and see, this strictly, you can show that the strict improvement in this. And because state and control spaces are finite, it has to converge in finitely many steps. But that number of steps can be exponential in state and the dimensions, and people are trying to beat down the exponent. That's like Shivram Kalyan question, if you know, IT. So he has a lot of work on sort of massaging the algorithm to reduce the exponent. Okay, so I don't know if I'm going on time, but okay. So yeah, so this is stochastic approximation with Markov noise. So the original algorithm of Robbins-Monroe in 1951 did not have Markov noise. That probably came in mid 70s or something. So this is the algorithm. So suppose the y is not there. Okay, so hxn plus mn plus 1. Okay, first let me just complete all the description. So the n is some slowly decreasing step size satisfying this condition. Sum of n is infinite and sum of n square is finite. So something like 1 by n. Mn is the what's called the martingale difference noise. Don't worry about the jargon. It just means that Mn plus 1 is some zero mean random variable which is uncorrelated with the entire past. Okay, that's take any function of the past up to time n, Mn plus 1 will be uncorrelated with it. Now, Yn is Markov noise in this sense. This is just a definition. It's kind of like a Markov chain, except that the transition probability depends on the current rate. This I'm going to drop. Actually, this is excessive generality for what I am going to use. So suppose Px has a unique stationary distribution mu sub x. So this is the main thing I want to use. Under reasonable condition, this tracks the Xn tracks the asymptotic behavior of this differential equation. So let me backtrack a bit. So in Robinson, original Robinson, Yn plus 1 was not there. So just Xn, Hxn. Their problem was to solve find a zero of x, solve the nonlinear equation Hx equal to 0, given noisy observations of x. So you have a black box which given input x spits out Hx plus noise. And then they came up with this recursion. So Xn plus 1 is Xn plus n times Hxn plus Mn plus 1. And they showed convergence of Xn to 0 of H in probability. Then later on people improved it. The one intuition is that you can think of this if n was fixed. Suppose Mn plus was not there, so Xn plus 1 is Xn plus 8 times Hxn. That's the Euler scheme for solving the differential equation x not equal to Hx. So this is a noisy Euler scheme with slowly decreasing step size. Okay, so think of the algorithm as a noisy Euler scheme for solving a differential equation with decreasing step size. So given that, so why these two conditions can be interpreted. So suppose Mn plus 1 is IID zero mean Gaussian. Okay, then this condition will imply that sum of n Zion plus 1 converges almost surely, because the total variance is finite. So the same thing happens here. You can show that under reasonable condition that sum of an Mn plus 1 converges with probability 1, which means the tail of that summation is going to 0. And tail of the summation is total noise you add from time n onwards. So there's less and less noise to worry about as time goes on. So the approximation, the noise level for the ODE approximation improves. And it also implies that n is going to 0. So the discretization error also goes to 0. So ODE approximation becomes better and better. And this sum of n equal to infinity means that you are simulating the ODE on the entire time axis, which is important because you are trying to capture its asymptotic behavior. So the advantage of this approach is that given some ODE whose properties you know, convergence properties, etc., it's a template for an algorithm. Any questions? I don't know if anybody following at all. Okay, so here the extra thing about what I call Markov noise is that is extra averaging of the Z was what was Yn plus 1. That just gets averaged with respect to the stationary distribution. And this is something common in applied mathematics. If you have two time scales, anyway, I'll talk about it later. The slow time scale sees the average behavior of the fast one, and the fast time scale sees slow time scale as something frozen more or less. So if you are sort of walking on the sidewalk slowly of a highway where the cars are going very fast, you just see a general sort of buzz of lots of cars going, and you will have some average kind of interpretation. Cars are going at this rate or whatever. You don't track single car. On the other hand, the driver in the car just sees some character on the sidewalk, not even clear whether he is walking or not if we are walking slowly enough. So you can treat him as a frozen entity, it doesn't matter. Okay, so if this I already said, if P is independent of the subscript, then there's just Yn is just a Markov chain and you see the stationary distribution. And the thing is, this is what is true is that the differential equation is some kind of finitely many asymptotic behavior, then the algorithm tracks them. And okay, The interesting thing is that if it's unstable equilibrium, it won't converge to it, assuming the noise is rich enough in all directions. The simple reason is that you get kicked out of, so suppose there's a saddle point or something, that means there's some stable direction you will converge there. I think there's one worthwhile figure which probably I should have included. So suppose this is a some equilibrium and there are some stable directions there, so there is what's called in, if it's a nation of system, there's some kind of low dimensional manifold along which you may converge there, and another manifold along, they correspond to the positive and negative, look at the eigenvalues of the linearization of H here, Jacobian of H, and the eigenvalues which are in negative half plane, the real value is negative, correspond to the stable, and the others correspond to unstable. But the thing is that what happens if you are not on exactly on this, you do this. And the basic message is that unless you are exactly on the stable manifold, you won't converge there. So if you have a good enough noise in all directions, you get kicked off it often enough that you don't converge to any unstable limit. So you can ignore unstable limits and worry only about noise. For example, if you are doing stochastic gradient descent, there's good enough noise, you won't go to a saddle point or a local maximum, but you can go to a local minimum. Yeah, so now I'll talk about the time scale I already mentioned. So suppose you have this two time scale algorithm, same algorithm, except some steps are on I mean, I use two different step sizes with Bn by n going to 0. That means Bn is asymptotically negligible doesn't compare to n. So the second iterator moves much more slowly. If you think of the OD limit, that OD will be on a much slower time scale than the first. So you can guess what's coming. Okay, so before that, there are actually three time scales because I also have the Markov chain. So the Markov chain moves on the usual clock, 1, 2, 3, 4. You can think of the xn iterates as moving on the time scale tau n. You treat an as a time step, then tau n is the sum of am up to n minus 1. So xm moves on this. This time scale is slower than the natural time scale, but it's faster than the time scale of Bn. These are both time scales of the algorithm, the two parts to the algorithm, slow and fast. But the entire algorithm is slower than the natural time scale. This is the fact I will use again and again. Yeah, so this is what I'm saying. So example, if an is 1 of the order 1 by n, bn is of the order 1 by n log n, the natural time scale just is n. The fast algorithm time scale is like log n, and the slow time scale is like log n. And this is what I said. Each time scale sees the slower ones as quasi-static. So the natural time scale sees the entire algorithm as quasi-static. And which algorithm says time scale sees the faster one as quasi-equilibrated. That means you see only the average behavior or equilibrium behavior. So the way to analyze this is that you average out the faster part of the algorithm with respect to the stationary behavior, and keep the slower ones as frozen like a fixed parameter. This will talk about the, I think I'm doing okay on time. Yeah, that also means that I'm going too fast. So any questions? I mean, anything you did not understand, I can repeat or add more details. If you get the intuitive picture, that's good enough actually. After you have sort of internalized the techniques, they become routine. I mean, so all the theory which I'm rushing through is actually a plug-in kind of a thing. Once you have learnt it, you just plug it in. You don't have to remember where it came from. Okay, so we will talk about some reinforcement learning algorithms. So this Q learning is kind of, okay. So we had that dynamic programming equation for value function V. So on the right hand side of that, yeah, so you look at the right hand side inside of the minimum. So what the entire thing which is being minimized, I call that Q. Okay, this function of U also, so Qi comma U. So Vi is minimum or U of Qi comma U. That's just another way of stating this. simply by giving the right hand side another name. But what happens here is that because V is minimum over U of Q. So so this is the definition anyway. The definition allows me to write an equation for Q itself, which definitely has a typo. That first min U should not be there. There's only one minimum, so this is a mistake. This is a mistake. This shouldn't be there. So the important thing is that in the first equation, the value iteration minimum was outside the average with the conditional average. Now the minimum is inside the conditional average. Okay, so now that the average is outside, what stochastic approximation needs is that average be outside of nonlinearity. Now I can write a stochastic approximation for this. Yes, so, okay, so this is Q value iteration also, like value iteration, I can write a Q value iteration. And then the stochastic approximation analog is what I have there. So what I have is that here, what I have done is, so you take this object, I remove the conditional expectation, then I have just this left, and I plug in an actual evaluation at the next state. Okay, so I am running a simulation. Instead of the conditional expectation, plug in xn plus 1. The distribution of conditional distribution of xn plus 1 is given by exactly this p. So replace the conditional expectation by an actual evaluation, but then I have to see the average also. So what I do is replace this, make it incremental. That's the terminology used. Make it a convex combination of a previous iterate and the corrected term at an evaluation. So this is a stochastic approximation algorithm now. So this is how you go from a recursive algorithm involving averages to a stochastic approximation. So I just reorganized the terms, put all the n terms together so that minus n qn is gone to the end. So this will converge to the stochastic differential. This will track a differential equation which converges nicely to the desired solution. So that yeah, maybe I won't get into that. In case of the discounted problem, this is actually you can do similar things, and the differential equation is easy to interpret. It's kind of, so if you are dynamic programming, for the discounted cost, dynamic programming is of the type equation is x equal to fx, where f is a contraction in the sense that infinity norm of fx minus fy less than equal to alpha times infinity norm of x minus y. And the ODE ends up being x dot t equal to fxt minus xt. And because f is a contraction, you can show that it goes to its unit fixed point. In fact, the infinity norm of xt minus x star solves as a Lyapunov function. Now, for this is harder, because average cost is not a contraction. The person who started it, C.H.C.J. Watkins. I have memorized the name, Christopher Helaby Cornish John, maybe, Watkins. I don't know. Some people believe it is for quality, but I'm not sure if that was the original motivation. We might have just, these are the PhD thesis. For all PhD students, take some inspiration. This was a PhD thesis in University of Cambridge. Yeah. Hmm. No. See, Q learning is, if you are doing deterministic recursion, this is certainly worse, because you're blowing up this domain, right? I comma u. That's only I. But this allows for stochastic approximation. No, you cannot do stochastic approximation directly for with the min sitting outside. You cannot do. You need averaging, right? Outside the nonlinearity. There it's inside the nonlinearity. Yeah. The next algorithm I talk about does do value iteration, but there's a different trick used. That also blows up the dimension in a different way. Anyway, where was I? Anyway, see, I'm not claiming this is sort of one of my works, but I'm not claiming that I'm the first person to prove convergence of pure learning. We're the first to do it for average cost, for discounted, etc. I think immediate after Watkins came up with this thesis, the first probably completely rigorous proof is by Watkins and Dayan, came immediately afterwards. Yeah, it doesn't have, so actually what, I'll tell you, so what you do is that I had this Vi naught, right? No, that only will have unique, but see, if I write Q dot equal to, it has this form, effect FQ minus Q minus, say, and let me write Q I naught U naught times the constant vector, something like that. Now, if I replace, this will converge to the algorithm, will converge to the Q for which this is beta. If I replace it by beta, that does not have unique solution. It will converge to a line depending on where you start. But that equation is easier to analyze. So what one does is analyze that equation. So that's not a contraction, it's a non-expansive. So it doesn't increase the norm. So using that, one can prove that Q dot equal to FQ minus Q minus beta times the constant once does converge to some point. Then the next thing is to argue that the trajectories of this equation can be expressed in terms of trajectory of that. And they converge to a same point. So, some time change and so on. I think I've been through this. Yeah. So the next one is actor critic algorithm, where you actually, now I'm doing directly with V because the policy is updated on a slower time scale, so you treat it as a constant. So this is a linear iteration, quasi-linear. Yeah, so I have not given the slow I mean, the slow iteration is non-unique. I mean, there are many possible ways to do that. So again, use the two time scale ideas. So the fast, the value function evaluation is called, the guy is evaluating you, so it's critic. So that's treats policy as a fixed parameter. So it's a linear, like a Q-learning kind of thing. So it converges, but it will converge to the value corresponding to the current policy. So the Vn will track V sub pi n, where pi n is the current policy, and then the policy iterate takes that as an input and minimizes that. So sort of Q-learning is inspired by value iteration. Actor critic is kind of inspired by policy iteration. There's also critic actor where you interchange the time scales. That will mimic value iteration. It's also policy gradient. So this is basically stochastic gradient. Policy gradient means you are just, in this case, just to minimize doing gradient descent to minimize beta. But then the gradient of beta needs computation. It's not explicitly known. So then you run some other algorithm to estimate that, and again it becomes a 2 time scale scheme. Okay, then there are also these are all tabular schemes, except policy gradient, and there are other schemes just for function evaluation, like TD lambda, LSP lambda, etc., where you fix the policy and estimate its value function using linear function approximation, and they are easy to analyze using this approach. And DQN is something mysterious. That's the deep Q network. That's not provably correct, but everybody says it works. Google says it works. So you better believe it. Okay, so let's see. Yeah, this is what my main current interest, or one of my current interests. So the RL RL algorithm basically assumes that you are observing state, right? Xn is at least thought of as a state. And so that means you are looking at a Markov chain. That was a sort of basis to even start. Now, if they are very large, you may use for few, sort of features for function approximation, etc. But basically, some Markovianity is taken for granted in the background. Now, the thing is, what if it is not Markov? Okay, so then you are making some error, and what is that error? At what so my effort is to try to understand what happens if the underlying process is not Markov. Okay, this one part of it has already appeared with multiple students, and the second is not yet written. So what's new is the second part. So I'm going to eventually look at asymptotic anyway. So I'll take the time starting at minus infinity, and I'll assume that they are all. So x sub n is the entire history from minus infinity to n of xn, and similarly un. Zeta n is both xm and um minus 1, and zeta bar n is xm um. Up to the reason I make a distinction is un is chosen at time n. So at time n, your information is x up to time n and u up to time n minus 1. So in the proofs, one has to work with that more often than with the bar version. And I will assume that the dynamics is time homogeneous in the sense that see, you can always write the probability joint probability law recursively, that conditional probability of the next given that of the entire past. Of course, if you start at minus infinity, uniqueness, etc., is an issue, but I'm not getting into that. So I assume that this function p now it depends on the entire past. That is that's time independent. So objective is the same as before. Okay, here I took cost depending on the next state. That doesn't matter much. And suppose I take what's called stationary randomized control policy. At time n, I choose un, control un, depending as a function of as the deterministic function of the past. Sorry, as a random function of the past. Okay, but no time dependence. Then one can argue that this class of controls is enough. And that kind of the way to do this is to treat, see, once I can consider the entire past of any process, that's a Markov chain for free. You can convince yourself. So this zeta n etc. are Markov chains. And sorry, zeta bar n is a Markov chain. Zeta n is a controlled Markov chain along with un. And then there's a standard way to argue that one can show by classical methods that this kind of control is sufficient to consider this kind of control. I'll simplify it further later. And also, I assume that now that everything is kind of time homogeneous, I assume that we are in a stationary what's called ergodic regime. So I'm at this infinite future. Only I'm looking at asymptotic behavior. So I'm at t equal to infinity, say. So I'll assume that everything is stationary. This can be justified also. So I'll do that later. And then look at what's called a marginal distribution. That is pi of a is probability that xn in a. So because of stationarity, that's independent of n. Okay. Now I define a controlled transition kernel Q, which maps x comma u to. So this is like a Markov chain kernel, where Q of a given xn un is. I'm just taking conditional expression given of a conditional probability of a given xn un. So I take the conditional probability of a given the entire past, and then take another conditional expectation given just current state, current control. This function, because the way it is defined, is a potential transition kernel, transition probability function for a Markov chain. It's state control to next state with some probability. Okay. And then it's easy to check that, I mean, just the way it is constructed, the Markov chain will also have pi as the stationary distribution. I'm going to skip the proof, it's there. So it's not hard if you are used to this kind of calculation. So now let x tilde, so I have this xn un process going from minus infinity onwards, which is not Markov. Just by looking at xn un xn plus 1, I cook up a, I just look at the conditional distribution of xn plus 1 given xn un. Okay, that defines automatically a transition kernel, which is independent of n because my whole process was stationary. Now I construct a Markov chain x tilde n with this transition kernel. And the claim is that they have these triplets, xn un xn plus 1 and x tilde n and u tilde n x tilde n plus 1 have the same law, same distribution. So in particular, the cost C dependent on xn un and xn plus 1 will be same for both. Okay, for the original non-Markov process and this Markov process. And this is the main claim. So now you can, now that I have said the main thing, Rahul, you can sort of tell me to stop anytime because this, okay, so this was the main thing I wanted to claim. So this is kind of mimic, the non-Markov is mimic. So when you run a Q-learning for the non-Markov process, actually doing Q-learning for the equivalent Markov, control Markov chain. So it solves the problem for the Markov chain, not for the original. Yeah. I mean, it's a legitimate Q-learning algorithm, but not for xn, for x tilde n. Okay, so the proof uses the fact that the zeta n is a Markov chain, and that maybe I'll skip this part. It's just that it's infinite string, but still a Markov chain. So when you have Markov noise, so that yn gets replaced by the zeta n. So, you see the transition kernel, the algorithm averaged over the past. So only the current thing is left. No, what I'm saying is that you think that xn is a Markov chain and you implement it anyway. Okay, the algorithm is for control Markov chain. You plug it in. Now, if the chain is not Markov, if the process is not Markov, the algorithm is still a legitimate algorithm for some Markov chain, which is not the original process, but it matches the triplet in distribution. Well, explain the main idea of the proof. So this is actually a caveat here somewhere. No, the next slide. Yeah. So it's not without problems. So the thing is that, see, this averaging is on the fast time scale, and either your algorithm 1 time scale or 2 time scale, they're both. Sorry, let me backtrack. The Markov chain, the process, not the process xn or the Markov chain zeta n is evolving on the natural time scale, which is the fastest. So regardless of whether your algorithm is pure learning, which is a single time scale, or actor critic, which is 2 time scale, both of them are slower than the natural time scale. So both of them see the average. That's the thing of the entire past. Now this is again this theoretical claim. There are multiple catches. One is that you also in Q learning you choose. See, the Q learning offline and online are very different. In offline case of Q learning, you can use any sampling distribution you want. You can choose IID if you want. All that is required is that with the function of IID, it learns both. Only requirement is that for any pair I comma u, it should be sampled frequently, in the sense that the relative frequency, the number of times you sample a particular IU till time n divided by n should be bounded away from 0 from below. So once that is satisfied, the algorithm will converge. How fast it's is a separate issue, but it will converge. No, I'm just saying that it's possible. The algorithm is such that if it's offline, you can do sample any way you want. It will work anyway. No, more stronger than infinitely often. Frequently, the relative frequency should be positive. Actually, it has been showed. It's a very impressive paper by Huizen Yu and Bertsekas for stochastic shortest path problem, where they proved that infinitely often is true, is enough. It may be true for other problems also, but nobody has proved them, and it's not clear whether it's worth it, because even though in principle something, suppose I update something every 2 to the nth time, even if it in principle it is okay, practice it may be worthless. But if you don't see something infinitely often, you are clearly not going to learn it. So it's certainly needed. Yeah, so the catch is that this uses a lot of continuity assumptions. And so if I use epsilon greedy policy for Q learning, that's online. So offline is you can do what you want. Online you cannot. You are trying to be close to the optimum. So with probability epsilon, you choose you control uniformly at random. It's 1 minus epsilon, and you choose the optimal guess for the optimal choice, the minimizer of Qn, Qn I comma dot. Okay. Now that minimization is over discrete collection. So it's jumping. If the minimizer is not unique, etc., there's no guarantee that it's moving smoothly. So this theory won't apply. So the one you can massage it, you can minimize over policy, as in policy gradient schemes. You optimize over policies and you add some quadratic penalty or something to make it strictly convex and so force it to move nicely with time. But this is one thing you have to keep in mind. The other thing probably not mentioned is that, okay, yeah, it comes here. So there's now is the paper with Chandak et al., which is already published, we actually have a concentration inequality for some time n onwards. So it's kind of tail concentration inequality. How? So you have this ODE limit. You take the epsilon tube around the ODE with high probability you remain in it. So you have the bound on that, and you can the error bound sort of splits nicely into some of individual terms. One is discretization error, then error due to martingale noise. And what's new here is that also an error due to non-Markovianity. And it is what you expect it to be. It's a conditional expectation, difference of conditional expectation of the Q trait given the entire past times, minus the same conditional expectation given only the current data. So how good this equivalent Markov chain will do depends on how good the one-step conditional expectation mimics the entire conditional expectation. So it will depend on the mixing properties of the process. If you don't depend on the past too much, then you are not doing too badly. Otherwise, that error can be very bad. It's a very slowly mixing process. Yeah, so use this to, there's some, we philosophize a bit in that published paper. The claim is that instead of using features with the standard folk wisdom, use a recursively defined features. Or so the thing is that features means you are just taking some functions of the state or state and control. So what I claim is take some dynamical system like this. So Jn depends on the previous Jn plus 1 depends on the previous Jn and the current control and state. And this is, take this dynamics to be low dimensional and use this as a state. And yeah, so this is what I just said. I'll just skip. So this is something we propose. So you feed this state observation and control to some encoder. This is just we claim some analogy with autoencoders. I'll tell you what the difference is. So take the state observation and control to some encoder, and that spits out the next state basically. The idea is that your Sn is the encoding of the dynamics. The low dimensional dynamical process is the encoding of the full process. And take that to a predictor and predict the next state. So it is more a predictor than autoencoder because I'm not matching output with input. I match output with the next state. Because it's dynamics. Autoencoder is for a static situation. So I'm feeding in something, I match what comes out not with the input, but with what the input is going to be in the next time around. Yeah, so